Okay. Okay, so actually, I'm very happy to see that your presentation's actually doing very well, better than I have expected. I'm a little bit worried, because this is the first time that I have ever delivered this course in English, and uh, given that you do not have too many, you don't really have the MIS person with you, right? So in the Chinese class, I actually have a lot of MIS students within the team. So it's like, but I can see that even though you don't have too many programming experience, you already have some capability to look into the data and use data to make strategy, right? That is the thing. Yeah. As I keep saying that the course is divided into two halves. The first half is about exploration, right? Data exploration. And exploration is for strategy. When you explore, you want to see the structure, you want to see the pattern, you want to see the trend that within the data, right? So the thing that you use, the information that you use to make your strategy is basically group information, right? Age group, area group, product category, and you use the group mean, you use the average to make the strategy, right? But today, in today's marketing, actually that is not enough, right? In today's marketing, we actually want to make a model to predict, to do prediction, and then use the prediction to do simulation. Like, for example, I would like to, so for the rest of our course, I will design it in this way, right? First of all, we will spend like this week, the rest of this week, and actually next week for probability, right? You already have a probability cost, so I will avoid what already been told in that course, okay? But don't worry too much, because we don't really in business analytics, we don't really use too much statistical testing, the theoretical testing, that type of thing. Basically, we use data for prediction. We use prediction for simulation. That is basically what we are doing, right? So I would like, in this 2 week, I want to give you the feeling of how to use probability, how to use model, how to use model for prediction, and then how to use prediction for to do simulation and make decision. Yeah. Okay, let me say it again. How to use data to do model, how to use model for prediction, and then how to use the prediction for simulation, and then use the simulation, use the result of simulation for decision making. That's what we want to do in this week and next week, right? And then I'm going to teach you two important model. The first important model is to predict values. For example, if I want to predict if a customer go back to buy, right? Well, what is their expected amount of buying, right? I have expected value, right? If this person come back to buy from me, I actually have the model to predict how much he will buy, right? That's one thing, right? We want to predict the value. And the second thing we would like to predict is to predict the probability, right? I also want to predict for each customer in what probability that this customer would buy from us next month, right? Okay? For every month, at the end of every month, I actually do two predictions on every customer. I mean, it's no longer a group, right? In the second half of our course, we will actually use model to do prediction on every single customer, right? Okay? And we actually have the technique to do some prediction on every product items, right? Okay? So this is different from exploration. In the second half of the course, we are going to use model to do prediction on every individual, right? Okay, so that's the key difference. So I'll spend like 3 weeks talking about how to build linear regression model, and that's for predicting quantity, okay? And I will teach you how to build logistic regression, and that's for predicting probability. And then using these two types of regression, we will do a things called customer value management, okay? Customer value management, okay? And that is actually in your presentation in the last hour, you already used some idea about customer value management, but you did not have the mathematical tool to do it precisely, right? Okay, so we will do that, and then for the last 2 weeks, of course, we will have 1 week for your final presentation, right? And I think we have 1 week left for kind of like a review, right? Try to connect every piece of analytic technique, analytic tool. Try to connect analytic tool to build up a business logic, right? So that's the plan for the rest of the course. Okay. So today we are going to start with probability, and so you know what is probability, right? Okay. Do you, and you know what is distribution? Do you? Okay. You should, right? But if I ask you to define what is distribution, it's still difficult. Okay, right? And if I ask you to do some operation on the distribution function, it will still be difficult. So this week and next week, I'll try to like give you some teaching notes so that to help you to do the probability, to do the distribution operation in the R environment, right? Okay. I'm not going to teach you probability from scratch, right? What I can do is I would like to teach you how to operate probability, how to operate distributional function in the R environment. That's what I can do for you, okay? Now, so probability, it's actually simply put, it's actually just a ratio, right? Probability do not have a unit, right? Probability is a ratio, right? It's a ratio that some event will happen in repeated random trial, right? By means of random trial, I mean that the trial has to have different outcomes, right? Okay, and that different outcome must be like occur randomly, right? So if you do not have uncertainty, you don't have to do probability, right? But in the real world, in the business environment, we have so many uncertain things, right? So that makes probability important because they are uncertainty, so we will have different outcomes. We do not know which outcome will come out, but we can estimate what probability each outcome will occur, right? That is the spirit of business analytics, right? But let me say it again. As a manager, you need to make decision under uncertain circumstances, right? Okay, so you want to make decision before you know the outcomes, which outcome will occur, right? We do not know which outcome will occur because it's uncertain, right? But we can estimate the probability of each outcome, right? And based on that as a prediction, we actually can make decision, can optimize our decision, right? So that's the logic, right? So probability by itself is a ratio, okay, repeated random trial. And then these are more more conceptual and more difficult, right? So Actually, the random trial is a random experiment in the jargon of statistic textbook, right? We define a random experiment. For example, I roll a dial. I roll a dice, right? I flip a coin, right? I have a bag of beans, red bean and yellow beans, right? And I like randomly pick up like five. Then how many red beans do I have, right? That type of thing is called random trial, right? Okay, you have random trial. So we have some way. The outcome of the random trial is we can define a random variable to represent the outcome of the random experiment. Okay? It's basically just to make probability easier. You need to do math, right? Okay? And you want to do math, you need to have some entity. You need to have something so that you can do the math, right? So so you need to define variable, but this variable is different from the other variable in that they are random, right? Okay, this is the variable, but its value vary, right? So it's called random variable. Okay, so so if the value of the variable varies, then how can we describe its value? I mean, you learn algebra, right? The basic algebra. So in algebra, every symbol, right? Every symbol is a variable, right? And every variable has a value, right? And that value in algebra, in simple algebra, should be fixed, right? It represents some fixed value, right? But in probability, it's different, right? The variable is there, but the value of that variable like vary, right? So it's called variable. Okay. So how can we do calculation, right? How can you describe a variable when its value like change? How can we do that? How can we describe a value that change within a range, right? Suppose you know the range. The way we described how a variable vary is called what?
Standard deviation.
Sorry?
Standard deviation.
It's called distribution, but it's not standard deviation. Okay. No, the label that it vary is called standard deviation, right? But if we want to describe how a variable vary, right, within its range, it's called distribution, right? It will be something like this, right? Histogram is actually a distribution, okay? Because it describes how the weight is a numerical variable, isn't it? Right? And weight can happen it's a real number, right? So it actually could be 45, 45.5, 45.555, okay? So every value is possible, but its range, it actually has a range, right? And it varies within this range. And in some range it has a higher probability, right? In some range it has a lower probability. And this entire thing is called a distribution, right? Okay? That's basically what you need to know before we go any further, okay? So you know what is a variable? We know that distribution is to describe how a variable varies within its domain, within its value range, right? Okay? And the last thing that I would like to define is called probability density, right? anyone can explain what is the probability density and how is it different? What is different between probability and probability density? Anyone can tell? What is probability density? Now, let's do easier things. You know what is the population density, right? What does it mean by population density?
How many people live within a certain
Within certain area, right? Per square mile, the number of people per square mile, right? Isn't it, right? And in the in chemistry, we call that the density of some particle, right? We are actually counting the number of particle per cubic centimeter, something like that, right? So when we say density, we actually has area, right? Okay, so let's have an example. Now in this histogram, right, we see that the beam width is 5, right? Okay, the beam width is 5. And if we plot it in density, right, if you use the y-axis as the density, then the way it works is that if you want to know the probability that the weight will fall in 55 to 60, okay? If you want to calculate the probability that the weight fall in this bin, right? Now, the probability is actually, now this is the y coordinate, right? The y coordinate is 0, 0, 6, 9. So it's actually 0, 0, 6, 9 times 5, okay? So density is actually, you need to time the density, you multiply the density by its base, okay? You multiply the density by its base, then you get the probability. You get my point? Okay? It's density, so it's actually the probability per unit x, right? If we are talking about a variable called x, right? So density means the probability within a unit of x, okay? So that is what density is, okay? So you might still have some confusion, but that's basically how it works, right? If you want to know the probability of this bin, right, which means that if you want to know the probability that weight would fall within 55 and 60, you need to you need to multiply the density by the base, right? Then you get the probability, right? So the probability that a weight would fall into this range is actually 0.345. Okay? You got it? Okay, that's good enough. That's good enough for probability. Okay? Now you know what is probability, what is random variable, right? What is distribution, right? What is probability density? And that is good enough. Okay? So the next thing I would like to do is, because today we don't have too much time, right? So my strategy is actually I would like to walk you through a case. Okay? I would like to walk you through a case. Try to connect from data to statistic, to visualization, to model, to prediction, to simulation, to decision. Okay, this is only one case, very simple case. But in this case, you went through all of the steps, okay? Now the case is here. If you go to today's, today we are in 8, right? So try to open this one. There's an interactive Shiny app. See that? Open the enfast2.rmd, okay? Open that. Just click it, and you will like bring up something, okay? If you bring it up successfully, you will see something like this. See it? You see it? Okay? Okay, right? Anyone have problem bringing up this app? No problem, right? Okay. So it start with the story, right? So this is YouTube, right? And you know this, right? And people from America, you must have noticed, right? So this in America, there's a park called Yellowstone, right? And in the Yellowstone, there's a geyser. Geyser is a thing that like this.
Video.
It's a periodical geyser.
Andrew, what I tell you about that?
So
Oh my.
so you erupt for some time, and then you will stop, and then you will erupt again, and then you will stop. Okay, so it's and because it is very trustworthy that it would like erupt and stop. So it's called Old Faithful. This geyser, okay. So we have some data about this geyser, okay. Here you can see that this is the eruption time, and this is the waiting time in minutes, okay. So this is the Old Faithful fountain, eruption time and waiting time, okay. So this is first eruption, second eruption, the third eruption, and we have a total of like, I forget, it's 272 eruption events, right? So this is the data, okay? And from this data, if I would like to like predict what is the next eruption time, what can I do? Okay, that is the question. Okay, so this is the data. So if you simply look into the data, you actually do not have any idea, right? So you need to do some statistics, isn't it? Right? But if you only do the statistic, you will run into a problem. As you can see that the eruption time, the mean eruption time is actually something like 3.5 minutes, right? Okay? But if you actually look into the chart, right, you will see that around 3.5, there's actually nothing, right? So this distribution is not normal distribution, right? And if you get the data and you simply do the statistics, that statistic could be very misleading, right? Okay? So whenever it's possible, we should always do the charting, because charting is so easy in R, right? You just put it into ggplot, and I say that I want to use waiting time as X, I want to use eruption time as Y, right? Isn't it? I think you can see the interactive chart like in 3 lines of code, right? Okay. So in your presentation, I see that there's one thing that you can improve it. Is that you always use static chart, right? But in R, chart could be interactive, and that interactive chart is actually quite useful, right? Okay. So chart is good because chart will help you see the structure within the data, right? Isn't it? I can see that the eruption and waiting time is actually clustered into 2 groups, right? There's a long eruption, come with long waiting time, right? There's a short eruption, and it come with a short waiting time, right? So this Old Faithful, they actually have 2 pattern of eruption, right? Long eruption and short eruption, isn't it? Right? So chart is good because it help you see the data in the systematic, in a holistic way. So you can see the pattern, you can see the phenomena, you can see the structure. That is what we already have learned in data exploration, right? But now go back to the business situation that we'd like to solve, right? If you want to predict, if you want to have a prediction on what is the next eruption time, right? Chart cannot help you, right? If you have a chart, you cannot predict what is the next eruption time, right? You cannot do that, isn't it? Right? So you need to have some mathematical instrument so that you can, as I have written here, chart help to explore the phenomenon or structure within the data, but it cannot do numeric prediction or estimation, right? So that's why we need model, right? The model sounds scary, but it's a representation of data, just like chart, okay? It's a representation of data, just like chart. And better than chart is it actually can do numerical prediction and numerical estimation. That is what a model is for, okay? Okay? So, now, the interface that you're looking is called Shiny App, okay? So it's kind of like a storyboard, right? So in this storyboard, I will walk you through, as I told you, from data to statistic to chart to model, right? So let's get into model. Okay. So, let me, this chart is totally interactive, so actually you can, like, let me do some. You can play with it, right? Whatever you want. But in the beginning, it should be something like this, right? As I say, a model is actually a mathematical representation of a variable, right? Okay. Now suppose that we are, suppose that we want to, sorry. Suppose the variable that we are concerning is about the eruption time, right? Okay. So eruption time is, right? This column, right? Okay. So maybe the simplest model is actually just a thing called data rock. Try this. Data rock is these things, right? So data rock is very simple, right? You have the data and you put a mark on whatever a data point is, right? This is the simplest model that you can do, right? Okay. But mathematically, it's difficult, right? Mathematically, we will call this mark a post function, right? Because we have like 272 eruption, right? So here we have 272 mark, right? And on each mark, there is a probability of 1 over 272, isn't it? Right? And actually, for example, in this space, there's no mark, right? So there's no probability. So is that a reasonable model at all? I mean, this could be a model, right? Okay, I write 272 post function. So on the location of that post function, there's a probability of 1 over 272. Okay? And anything that that does not fall exactly on the post do not have probability at all. Is that reasonable at all? This is the data, right? Okay. So if I'm using a data rock model, then this model fit 100% fit with the data, right? If you measure it with the data, it would not have error at all, right? So it tied to the model, exactly tied to the model, right? Okay, but is it reasonable? What is the problem if I want to make prediction with this model? Actually, I can. If I want to do it, I can do that. I can do a CDF, right? A CDF is kind of like a integration on the PDF. You know what is PDF and CDF? Anyone need explanation? Raise your hand. Oh, okay, I'll do it. You should already. Okay, doesn't matter. I'll do it. Where's my slides? So this is the density function, right? Okay, density function. Usually we will call it PDF. Okay. I have a slide. Where is that? Here. Okay. It's called probability density function, right? So histogram is a kind of probability density function, okay? And here's another one. So for probability density, if you have the probability density function, okay, we will talk about how to make a PDF later, okay? So if you have a PDF, then you can estimate the probability in this way, right? If you do an integration on x1, x2, right? You do an integration on over the PDF on this range. Actually, the area under the curve is the probability. Okay? Exactly the same as like what I have explained it here, right? The area under the curve is actually the probability. This is called the density function. And it is useful, right? As long as you have where is that? Here. As long as you have this PDF, right? Then you can estimate the probability that an event would occur within a range, right? The numeric variable, every single point actually do not have a probability actually. For example, if I say that what is the probability that next eruption will be exactly 21 seconds? It's no probability, right? Because it will be either larger than 21 or less than 21. Exactly 21 is like virtually no probability, right? So in order to calculate the probability of a continuous numeric value, you need to specify a range, right? So when you have the PDF, you do an integration on that range, right? Then you get the as in this chart, the area that under the curve within that range is actually the probability that variable will fall in this area. Is that clear? Okay, so you know that what is a PDF, right? It's a mathematical function form, right? So by integrating this mathematical function form, you can calculate the probability that the value will fall within a range. Get it? Okay. Now, PDF is good, but this integration is actually difficult, right? Some PDF is very, very complicated. For example, like normal distribution, right? The normal distribution is already very complicated. And you want to do an integration on that, it's almost impossible, right? It's actually even myself, I cannot do integration on the normal distribution PDF, right? So a better way to calculate probability is to use CDF, right? Okay, so CDF is actually the integration on PDF. Okay, let me say it again. CDF is called cumulative probability function. Okay, so as you can see, the CDF always start from 0. Okay, its left tail is always start from 0, and its right tail always stop at 1. Okay, so at any point, it represents the probability that from the left tail cumulated to certain point, right? For example, here x1, we do into the CDF x1. CDF is kind of like 0.3. Okay, it's not very precise, but let's say it's 0.3, and the x2 CDF is like 0.9. Okay, so the good things of CDF is, if I want to know the probability between x1 and x2, I simply use this CDF x2, which is this probability, right? And CDF x1, which is this probability. So actually PDF, the y-axis of PDF is density, right? Okay? Here is density, but you need to integrate density to get probability. Okay? And because CDF is already integrated this PDF, so actually the y-axis of CDF is what? I mean, the y-axis of a PDF is density, right? As I told you, probability density. Okay? So you need to do integrate to calculate the probability. However, in CDF, the y-axis is already what? Probability, right? It's the cumulative probability from the left tail to a certain point, right? Okay. So if I want to know the probability within this range, I simply use the CDF at x2 to minus the CDF at x1, right? So with CDF, I can do that very, very easily, isn't it? Right? Okay. So this is CDF and PDF. Okay. Okay. Now let's get back to the case. So if I simply put a data rock, this PDF is actually not a good PDF, right? So for example, if I do a integration from this point to this point, I will see that there is 0 probability, right? And we know that it's wrong, isn't it? We know it's wrong because the reason that there is nothing occur here does not mean that there is no probability that the next eruption will not fall in this range, right? Okay, so the problem with this data rock model is that it's too specific, you know. It is too specific to the data. Okay? It tied to the data in a way that it tied to the, it's too tight. It's like too specific to be generalized. Okay, we are building a model, so the model, this is the data in the history, right? We would like to use the historical data to predict the future, right? Okay, future will be similar to the past, okay, but it will not exactly the same as the past, isn't it? Right? And if we do the model this way, the model would be exactly the same as the history, right? Anything that in the history does not happen, you cannot see it, right? You will treat that as no probability, and that is not reasonable, right? Isn't it? Right? Okay. So the problem of this data rug model is it is too specific and it do not have the generality for inference, for prediction. Right? If I want to do a prediction, I want this model to have some sort of generality so that I can use it to predict the future. I can use the data, I can use the sample to do a model. And what I want to do is use this model to predict something out of the sample, right? Let me say it again, okay? I use the sample to build a model, right? And the reason that I want this model, I don't want to use this model to predict the sample, right? Because sample I already know, right? I want to use this model to predict something out of the sample, right? So if this model is exactly the same as if this model is exactly the same as the sample, like this, right? It will be too specific to the data, right? And it no longer has the generality to predict something out of sample. It no longer have the generality to predict the future, right? That is the problem of data rug, okay? That is why we need a better mathematical form, okay, to help us do the prediction. You get the point? Okay? So usually we will use this type of things to, right, for visualization, right? To visualize the density, the PDF of numeric data, we used to do histogram, right? Okay? Histogram is better, right? Isn't it? Okay, so it actually has some generality, right? So the thing is if something happened here, then it, but to do PDF, right? There is a thing that you need to choose in PDF. It's called the number of bins, as you can see here. If I use you actually can control the number of bin in a histogram, right? Okay, by controlling the bin width, right? Okay, so if you do this is a histogram of 40 bin, okay? It's very detailed, right? But it has a problem, right? You can see this thing we call glitch, okay? This glitch is actually unreasonable, right? Because it doesn't really mean that in this bin width they are very high probability, and in this bin width they are very low probability, right? This pattern, it means that there are some, in this sample, right? In this sample, there are some event right? It just happened in this sample that you have this glitch, right? If you want to build a general model, you should not see this, isn't it? Right? You see my point? If I want to have a general model, then this unreasonable pattern should not appear in your model, right? So the resolution is actually try to reduce your, right? You can actually try to reduce your, you can do with me, okay? Because that thing is interactive, okay? So if you reduce the, we still see a glitch here, right? So so the bandwidth is still too narrow, right? So we can try to reduce the number of bins to a point that all of the glitches is gone, right? Okay, so this could be a good model, right? I mean you can use histogram to generalize the data, right? To build a generalized model for probability prediction, okay? But yeah, it's a good idea to do that. But only choosing histogram is not good enough. You also need to determine what is the bandwidth of your histogram, right? It looks very different, right? This histogram looks actually, if you actually do that, you will see that, sorry. If you reduce you can see that the shape of the histogram actually jump a lot, right? It jump a lot, right? Okay, until you go to a stable point, right? Isn't it, right? Okay, so histogram is a good idea to build a model for numeric variable, but to do it right, you need to adjust the bandwidth, right? Otherwise, you can still do a very bad model. Okay, I think it's 11:03. Let's take a break, and we'll be back at 11:10. Okay. So you can play with these things without problem, right? Okay, good. So